We've developed a lot of powerful tests for convergence and divergence, but they all have limitations. Divergence test only tests divergence. The comparison tests both of them. You have to know what to compare it to. The alternating series test is only useful, of course, for alternating series, etc. So we're going to develop two more tests, and actually, of all of them, these are the two that we're going to use the most in Chapter 11. Matter of fact, these are the ones we're really going to use a lot in Chapter 11. The ratio test and the root test. And I really enjoy the ratio test and the root test. I find them both very fun, but I'm kind of nerdy like that. All right, so the ratio test. Let's go. So if we have an infinite series, then we let R, ratio, R, be the limit as k goes to infinity of a sub k plus 1 over a sub k, absolute value of that fraction. If R is less than 1, then the series converges absolutely, and therefore it converges, because absolute convergence implies convergence. Right? If R is greater than 1, including if R is infinity, right? If R is any number greater than 1 and infinity, or infinity, then the series diverges. And there's only one inconclusive bit, and that's if R is equal to 1. If R is equal to 1, then the test is inconclusive. All right, so let me just write another little way to write this just to kind of help ourselves, because of course we're going to be taking fractions. So it's helpful. Oh, I turned that period into a equal sign, aren't I clever? All right, so this is equal to the limit as k goes to infinity of a sub k plus 1 divided by a sub k. That division sign right there can be written like that. And that's the way we're more used to writing it for when we have to flip and multiply, which is what we're going to do. So this is the big kahuna. This is what the ratio R stands for. And just a little reminder of some basic pre-algebra. There's no good ways to put it, so let me just put it right here. Recall that if you have a to the p over a to the q, that is a to the p minus q. You can imagine that might be coming in handy when we're doing divisions like this. Okay, so let's look at the first one. So I want to determine whether this particular series is convergent or divergent, right? Whether the series converges. All right, well, I'm not going to do a comparison test with this thing. It's not an alternating series, so that one's out. Lord knows I have no desire to try to do an integral test with this thing, because I don't know integrals with factorials like that. And the divergence test only tests divergence. So my best option is the ratio test. Okay, so to do the ratio test, I would let R be the limit as k goes to infinity. And then I'm going to take a sub k plus 1. Okay, well, keep in mind that this bit right here is a sub k, right? So a sub k is 10 to the k over k factorial. So a sub k plus 1 would be 10 to the k plus 1 over k plus 1, the whole thing, factorial. You have to put parentheses there because you don't want to imply that it's 1 factorial. So you need k plus 1 in parentheses. And I'm going to divide that by a sub k. So that would be 10 to the k over k factorial. And I'm going to take the absolute value of that. Right? So this is a sub k plus 1. This is a sub k right here. All right? Just want to change how I wrote that. All right, now of course, division with fractions. Now you can see why I wrote it that way. I mean, who wants to write this fraction divided by that fraction in one big fraction? That would just be annoying. So I wrote it that way. So now I'm going to flip and multiply by the reciprocal. So this would be the limit as k goes to infinity of 10 to the k plus 1 over k plus 1 factorial times k factorial over 10 to the k. Now I'm going to rearrange this. I normally won't bother with this step, but this is your first time, so I want you to see what's going to happen here. So limit is k goes to infinity of, and I'm going to put the two 10 to the k pieces together here. So I have 10 to the k plus 1 divided by 10 to the k. That's where that little rule right there is going to come in handy. Times, and then think about k factorial. K factorial means it's k times k minus 1 times k minus 2, and you would go, keep multiplying until you get to 2 and then 1, and you're done. K plus 1 factorial starts at k plus 1, then loses 1 and goes to k, then k minus 1, then k minus 2, all the way down to 3, then 2, then 1. Oops, 1. You're multiplying, right, all the way along. Oop, and then I have to close my absolute value sign in. All right, so now over here in this corner, think about what's going to happen. I have 10 to the k plus 1 over 10 to the k. So using this rule, we would take k plus 1 minus k, and we'd be left with, I'll write that out. So this piece right here is 10 to the k plus 1 minus k, which would of course be 10 to the 1, which is 10, right? So in other words, everything kind of divides away and you're left with 10. Now over here, the 1 cancels with the 1, the 2 cancels with the 2, right? The 3 cancels with the 3, 4 with 4, and so on. K minus 2 divides away with k minus 2. They're not really canceling, they're dividing and making 1, right? K minus 1 makes 1. K and k makes 1. All you're left with is a 10, or excuse me, a k plus 1 in the denominator here. So let me rewrite that. So that's the bit you're left with there. So now that would be equal to the limit as k goes to infinity of, all right, left in the numerator is 10, right? This is 10 over 1. The bigger part is on the numerator part. So it's 10 divided by k plus 1. Right, but we learned a long time ago that the limit of 10 over infinity, any number over infinity, is 0. That's your r value. Okay, but notice r is 0. 0 is less than 1. Therefore, this series converges absolutely. So this is less than 1. Therefore, the series that we were given, which was 10 to the k over k factorial, converges absolutely. And therefore it converges, right? So it converges absolutely, and therefore it converges. So you can just say converges. Absolute convergence implies convergence. The ratio test is really useful for factorials because factorials don't have easy ways to work with integrals and other things. But this piece right here, where everything cancels except for just one piece left over, that's very nice. And that happens a lot with factorials. All right, so now let's do it again. So we have b sub n here, which is, here, I'll just write it. This is b sub n. B sub n is 9 to the n over, that's a 9, negative 2 to the n plus 1 times n, right? So when I want to do my limit test, I want to take r, which is equal to the limit as n goes to infinity this time because my index is n. I'll see if I can remember it the whole time. All right, so, and then I'm going to take b sub n plus 1. So I need to take 9, instead of to the n, it's to the n plus 1, over negative 2 to the n plus 1 plus 1, right? So that n becomes an n plus 1, and n plus 1 would be n plus 2. And instead of n here, we'll have n plus 1, but of course I have to put it in parentheses. I'm going to divide it by b sub n, which is 9 to the n over negative 2 to the n plus 1 times n. All right, well, again, flip and multiply. Limit n goes to infinity, absolute value 9 to the n plus 1 over negative 2 to the n plus 2 times n plus 1. And then we would multiply it by n over n times, sorry, I got ahead of myself there. It's n times, so negative 2 to the n plus 1 times n, there we go, over 9 to the n. All right, now I can rearrange this a little bit just to kind of help with the math. So that's the limit as n goes to infinity of. All right, I'll put the two 9's together. That's 9 to the n plus 1 over 9 times negative 2 to the n plus 1 over negative 2 to the n plus 2 times n over n plus 1. All right, so this is the limit as n goes to infinity of, now let's think about this. The 9 to the n plus 1 and the 9 are going to go away and just leave you 9 in the numerator here. Just like over here, we were left with 10 in the numerator here. Matter of fact, I'm going to erase this here and make that clearer because it was 10 in the numerator. Right? This is larger than that. And then in the middle here, we have more in the denominator than we have in the numerator. There's n plus 2 down here, and there's n plus 1 here. So by the same rule, right, we'd take n plus 1 minus n plus 2, the n's would cancel, and you'd be left with negative 2 down here. And then over on the third part, n and n plus 1, there's nothing you can do there. Not yet. We'll take the limit of that in a second. So that means that we're going to have the limit of the absolute value of 9n. Well, let me do it this way. 9 over negative 2 times n over n plus 1. Right? Like that. Okay, so then let's think about this. That's a constant right here, right? This is 9 halves. Well, it's 9 over negative 2, but there's an absolute value there. So that's actually going to be 9 halves, the limit as n goes to infinity of the absolute value of n over n plus 1. But that's infinity over infinity, right? So by L'Hopital's rule, this would be L'Hopital. Actually, let me write that in yellow just to tie it to the infinity over infinity here. So that's L'Hopital's rule that we're using. Or technically, this is a rational expression. This is a polynomial over a polynomial. So we have it cheaped for that, right? It's built from L'Hopital's rule, but we know how this is going to go. It's going to be 1 because it's a polynomial divided by a polynomial, and therefore it's just the ratio of the coefficients for that polynomial. So that means that this will be the derivative of the numerator over the derivative of the denominator. If I'm going to use L'Hopital's rule, I'll go ahead and do it, which is 1 over 1. That means we have 9 halves. Ooh, sorry, I lost my over 2 part. That was a mistake. So it's 9 halves times 1. I got so excited about L'Hopital's rule, I couldn't stop. So therefore, that's 9 halves. 9 halves is your r. Oh, this is r. So r, remember all of this was equal to r at the very beginning. So r is equal to 9 halves, and 9 halves is greater than 1. I'm just going to box the whole thing. Erase that extra r in there. All right, greater than 1, let's go back to the ratio test. If it's greater than 1, including infinity, then the series diverges. So therefore, our series, which was 9 to the n over negative 2 to the n plus 1 n, diverges. My box got a little weird there.